we got a determinant of a matrix with lambdas in it, right? Tell me what equation we came up with when you do the determinant of A minus lambda I. What was your equation you came up with? Please simplify it and put it with the highest order first. Lambda squared, agreed? Minus lambda? Minus 2. When we factor it, we get lambda minus 2, lambda plus 1, right? Made it easy for you here. No need to go to anything else. If I'm wondering when it equals 0, to find out what vectors are linearly dependent, how many are dependent, to find lambda, lambda turns out to be 2, or lambda is negative 1. What does that mean then? What is ax minus, let's say, 2x? Let's go with lambda equals 2. Each eigenvalue has something happen. Each eigenvalue. Let's have the eigenvalue lambda 2 first. If we let lambda equal 2, what do we get? We get, putting this all, I guess I could put 2ix, but hopefully you guys are okay with this. I get the same thing as a minus 2I, agreed, times x. Let's write that out. So that would be, if I subtract 2 from the main diagonal, it'd become 1, negative 4, 4, negative 1. Take a sec, make sure you agree. I did 3 minus 2, negative 2 minus 2 on the main diagonal. Are we okay, or do you need me to write? I'll write it out. I don't trust that you guys understand. You may, in which case, do not feel insulted. I just want to make sure we're comfortable. And I'm subtracting 2 times the identity matrix. That's 2, 2, 0, 0. Normally, like I said, this is really lambda, lambda. And that's why we get 3 minus lambda, blah, blah, blah. That's where you came up with this thing. But we found lambda to be 2. So for any vector x, this is always 0. That's what Max said. That's what we talked about, right? Give me any vector. We'll show that this is 0. 1, negative 1, 4, negative 4. Give me any vector, 2-column vector, or 1-column vector. 2, 9, 9. 999? That's 0, right? Any vector makes this 0, 0. Because 9 minus 99 is 0, and 36 minus, I don't know, big number is 0. That's not right, is it? What went wrong?
Determinant.
Slow down a little bit. We have the time today. It's very important. What are we doing? To understand the meaning here is really why I'm breaking this apart and saying, what are we doing wrong? What were we trying to find? An eigenvalue. Some scalar multiple so that for any vector x, it won't move. Any vector? Any vector won't move. Any vector? Is that what I said? No, there's a specific vector, right? Which vector, singular, does not change. With each eigenvalue, there is an eigenvector. Okay, so I agreed with Max because I wanted us to go in the wrong direction. This was perfect. In fact, I was hoping to lead there. How easy it can be to mix up. Oh, linear dependence versus independence. The big thing is that alpha, why it took so much time yesterday. This vector is key. That negative 2, 3, 1, that's what makes it 0, right? What linear combination of those columns here will make this 0? Here's a column, here's a column. What vector x, what linear combination of these two columns will give me 0? And again, I should write 0, 0. We don't know, right? Not off the top of our heads. We probably should write it out. So, x is x1, x2. Do we agree? I don't know how much of this you need to write down. It's totally up to you. 1, 4, negative 1, negative 4 times x1, x2. I want to be 0, 0. What are my equations I'm getting out of this? x1 minus x2 equals 0, and 4x1 minus 4x2 equals 0. Agreed? A couple things before we go on. When you plug in an eigenvalue, do you see that the determinant of this is 0 as we'd expect? Because there's a linear dependence involved. Do you see that the first row is just 4 times this, or 1/4 of the second row? And that the first column is just the negative of the second column, or vice versa. The second column is the negative of the first. They're dependent as rows or columns. The column thing is what I want us to focus on for eigenvalues. So what's the relationship here? I've got a dependence, right? I can choose whatever I want. x1 equals x2, agreed? Using the first equation or second, they're the same thing. So Jimmy, here's what you could write. On the test, if you wrote x1, x1, or more specifically, x1 times 1, 1, that's your eigenvector. And you could use x1. But here's what I suggest. Let x1 x1 equal alpha. Okay? Again, that alpha idea just allows us to see, oh, it's a constant times 1, 1. So the eigenvector, the one vector that does not change, is 1, 1. Now, that eigenvector only goes with this eigenvalue. Okay? So, here's what you'd write as a solution when we're finishing this up, how we understand this. The eigenvalue, when it equals 2, the eigenvector is 1, 1. And if you put alpha here, that's fine. It's any multiple of 1, 1. That's the vector that doesn't change. 1, 1 will stay put. Maybe it'll become 4, 4 or 5, 5. Just to finally conclude so you feel some closure here, let's go back to our original matrix. 3, 4, negative 1, negative 2. If I multiply that original matrix by my eigenvector, 1, 1, what do I get out? 3 minus 1 is 2. 4 minus 2 is 2. Isn't that 2 times my eigenvector? 1, 1. Now clearly I've chosen easy numbers, as has the book, so that we can get the theory down. The reason, the proof, the why is why I spent so much time yesterday on that alpha concept. Questions? Why don't you go ahead and try to find the eigenvector for the other eigenvalue? Okay. What's the other eigenvalue? Negative 1. Try to find the other eigenvalue, the other eigenvector for the eigenvalue of negative 1. For eigenvalue negative 1, you tell me what your eigenvector is. Sorry, eigenvalue of negative 1, tell me what the eigenvector is. Brain, what is going on today?